let's wrap up our discussion of residual properties. Now, again, we've been talking about definitions that are in a dimensionless form, and we get those by dividing by RT for energy and R for entropy. We choose the units for R, which gives us the appropriate units that we would want for, say, Gibbs energy or enthalpy. And formulas that we have available to us are in terms of Z. These are some other formulas, and what we needed to do next was do the calculations, where Z is defined as PV over RT, but not the ideal gas law. That would be equal to 1, where PV and T are related through an equation of state. So let's look at the generic cubic equations of state. We saw these slides earlier in the course. Again, the main cubic equations of state can be written in this form. And these were the ways that the various constants were defined for that. And alpha for the SRK or the Pang-Robinson equation are defined here in terms of the acentric factor omega and the reduced temperature TR. If you use the cubic equation of states and use those definitions that we had, it turns out that G over RT is going to be Z minus 1 minus the natural log of Z minus beta minus QI. HR is this, again with the QI, and SR is this, again with a QI. Now, if we return to this other slide, we'll see that Z and beta and alpha, these are all things that, okay, I can, pick out from here. But what are this Q and I thing? Okay? Well, you do choose this based on the values of epsilon and sigma. When they are the same, we use beta over Z plus epsilon beta. And when they are different, we use the natural log of Z plus sigma beta over Z plus epsilon beta, all divided by sigma minus epsilon. Now there's an example. We're just going to go through it in the book. It's not terribly enlightening, so I'll go through it fairly quickly here. But you should stop and make sure that you can also get those same numbers and make sure that you understand where everything fits together. But we're just going to calculate the value of the residual enthalpy and the residual entropy for a particular substance, in butane, at a particular temperature and pressure, 500 Kelvin, 50 bar. We're going to do this using the Redlich-Kwong equation of state. So again, if we return back here, this is going to be the RK that I'm going to get right here. Okay, so I need to first find data, the critical temperature and pressure. I'm going to also need omega in a few minutes. I'm going to calculate, oh wait, no, I don't for the Redlich-Kwong. Okay, so I just need TC and PC. TR is the temperature over TC, so that it's dimensionless, so 1.18. The reduced pressure is the pressure over PC, so in this case 1.317. And then I use those throughout these various formulas. Okay? If you do this, then you can use the stuff from lesson 7 to find out that Z is 0.6850. Okay, that's in a previous lesson. Then I'm going to use that to figure out what Q is equal to, and there's the formula for that using these previous results, log of alpha, d log of alpha. It's very exciting, isn't it? You plug numbers in. We end up with HR over RT is equal to negative 1.08, which means HR in SI units would be, well, let's use 8.314 joules per mole Kelvin. Temperature is 500 Kelvin, and so negative 4,500 joules per mole. If I wanted to figure out for S, I'm going to do very much the same thing, use the appropriate formula. I get SR over R is negative 0.78735. Multiply by my choice of R, I chose 8.314 joules per mole Kelvin, and I end up with the residual entropy is negative 6.546 joules per mole Kelvin. Now there are some excellent examples available if you look in the links to other lessons where you can see some other examples of this in use. We will be using this again in future lessons. But at this time, this concludes our introduction to residual or departure functions.